Assalamu alaikum dear students of class 11th. As in the last video lecture, I have started a new chapter from your 11th standard physics textbook. That was chapter number 11, electric current through a conductor. And inshallah today's lecture will be part 2 of the same chapter. So in the previous video lecture, I have explained you regarding electric current and Ohm's law, which are the omitted topic for this year, and we are not going to ask you question based on these topics because these are the omitted topic, but it is necessary to understand this basic term that was electric current and the basic law that was Ohm's law, so that we can move further and it will help us to solve the main subtopics of this topic. So let's move further. So inshallah in today's video lecture we will learn about electromotive force. At first sight, the name EMF implies that it is a force that causes the electron, that is charged particle, that is current, to flow through circuit. In fact, it is not a force, but it is energy supplied by some active source such as battery to 1 coulomb of charge. But before start with this electromotive force, which is the subtopic, that is 11.11 topic of this chapter, let's see the learning objectives of this lecture. So by the end of the session, you will able to describe the electromotive force, that is EMF and internal resistance of a battery. Then you will be able to define potential difference, and you will able to explain the basic operation of a battery, and the last you will be able to derive an expression for maximum allowed current from an EMF device by using the application of Ohm's law. So let's move further. Voltage has many sources, a few of which are shown here. As you can see in these pictures, all such devices create a potential difference and can supply current if connected to a circuit. A special type of potential difference is known as electromotive force. So first of all, we have to see what is electromotive force. So the electromotive force is the total voltage induced by the source. In other words, it is the amount of energy supplied by the source to each 1 coulomb of charge, and it is measured in volts and represented by the symbol epsilon, or sometimes it is represented by capital E also. So actually this is not a force but a kind of energy. And which kind of energy? It is the amount of energy supplied by the source or by the EMF device. So this is the regarding electromotive force, and as it is measured in volts, so as you can see here, we are having the formula, that is EMF is equal to work done per unit charge. So simple definition of EMF is what? It is the amount of energy supplied by the source to each coulomb of charge, or it is the energy supplied by the EMF device, or what? How you can define it? It is defined as the work per unit charge. How work per unit charge? This we will see later on. So this is the basic formula for the EMF, that is work upon charge, and that is EMF at the symbolic form, it is epsilon is equal to, or E is equal to W upon Q, where W is the work and Q is the charge, and its SI unit is the voltage, so volts. So as you can see, it is nothing but volts. So this is all regarding the EMF. Now let's move on to the next term, that is potential difference. The potential difference is defined as the amount of energy used by 1 coulomb of charge in moving from one point to the other. How it is defined? It is defined as the amount of energy used by 1 coulomb of charge in moving from one point to the other. It is again measured in volts and represented by the symbol capital V. The potential difference is measured by the voltmeter. So if you observe both the definition of EMF and the definition of the potential difference, both the SI unit and both are measured in volt. So is there some similarities between them? See, both are the energies. The potential difference, see, as you can see here, regarding the potential difference, and the potential difference, the formula for this same is nothing but energy or work upon charge, that is W or E upon Q, and again it is measured in volt. So the potential difference and electromotive force both are the form of energy. Yes, one of the major difference between the EMF and the potential difference is that EMF is caused by converting the other form of energy into electrical energy, as you can see here. So EMF is caused by converting the other form of energy into electrical energy, whereas the potential difference is the electrical energy is converted into the form of other energy. So this is all regarding the EMF and potential difference. So EMF is the energy supplied by the external source or by the EMF device, and potential difference is the energy spent so that a unit charge can be circulate once round the circuit. So one is the energy supplied, that is the EMF, and another is the energy spent, that is potential difference. So hope you will understand the EMF, that is electromotive force, and potential difference. Now next to that we are having the third term, that is internal resistance. So basically internal resistance refer to the opposition to the flow of current offered by the cells and batteries themselves, resulting in the generation of heat. Internal resistance is measured in ohm. See, have you ever heard the word resistance? Recall the Ohm's law. Yes, in Ohm's law there was a proportionality constant, that was resistance, that was capital R. So what is the resistance? Resistance was nothing but opposition offered by the resistor, by the component resistor. So as you can see, if you are having a battery, see, this is nothing but a kind of cell that normally we can see it at, you might have seen this at your home. So this is a cell, and if you see the right hand side, or this is nothing but the internal circuit of this cell, where we are having a battery. See the terminal E, that is the EMF, and a internal resistance, that is nothing but the small r. So small r is basically referred as internal resistance, where capital R was nothing but the external resistance. Okay, so this is all regarding the EMF, potential difference, and internal resistance. So this is what I have defined you, all these three terms. So now let's move on to the circuit with EMF device. So here you can see this is the circuit of EMF device. A resistor capital R. Here the EMF device keeps the positive terminal at a higher. See, as you can see here, this yellow part, the yellow highlighted part, is nothing but the cell or the EMF device. This is nothing but the part of the cell, as you have seen the internal structure of the cell. So this is nothing but the part of the cell, or what you can say it to the EMF device. So this yellow part is nothing but the EMF device, and you can see the negative and the positive terminal. So B is the positive terminal and A is referred as negative terminal. So positive terminal at a higher electrical potential than negative terminal, that is the negative. The EMF is represented by, as you can see here, E from the negative terminal to the positive terminal when the circuit is open. So how you can say circuit is open when it is not connected to the, not connected actually. So this is called as open circuit. When it is connected, so it is called as closed circuit. So when circuit is open, that means there is a no net flow of charge carrier within the device, and when it is closed, when connected in a circuit, so there is a flow of carriers from one terminal to the other terminal inside the EMF device, that is inside the cell. The positive charge carriers move towards the positive terminal, which act as a cathode inside the EMF device or cell. Thus, the positive charge carriers move from the region of lower potential energy to higher potential energy. See, always remember it. Positive charge carrier move from region of lower potential energy to higher potential energy, which is cathode inside the EMF device or cell. Here, the energy source is chemical in nature. In a solar cell, it is the photon energy in the solar radiation. Now, suppose that a charge dq flows through the cross section of the circuit, as you can see in this diagram, in time dt. That is what? A small time. So at a small time, the charge will flow, that will be small, that is nothing but the dq. So it is clear that the same amount of charge, that is dq, flow throughout the circuit, including the EMF device. It enters the negative terminal, that is the low potential terminal, and leaves the positive terminal, that is higher potential terminal. Hence, the device must do work, that will be dW on the charge dq. See, if charge is moving, that means the energy supplied by the EMF device, so charge can move. When charge is moving, that means some work has to be done over there. So this work done is nothing but considered as dW, because charge is what? Small, that is dq, and at the time interval of small time interval of dt. So what we can say that EMF is nothing but dW upon dq, as we have seen the definition of EMF, that is the work done upon charge, that is work done per unit charge. So finally we can say that EMF is equal to work done per unit charge, and as we have seen that the EMF is measured in volts, so it can also be work done per unit charge. What is the SI unit of the work? SI unit of the work is nothing but joule, and SI unit of the charge is nothing but the coulomb. So what else you can do? You can say the SI unit of the EMF is nothing but joule per coulomb, because the formula for the EMF is nothing but W upon Q. So in an ideal device, there is no internal resistance to the motion of charge carrier. If there is no internal resistance, so this is an ideal device where there is no obstacle in the flowing of the charge. The EMF of the device is then equal to the potential difference across the two terminals of the device. Always remember, potential difference is always measured across the two terminals of the device. So when there is no obstacle, where there is no resistance, so EMF will be equivalent to the potential difference. That is, E is equivalent to V. Yes. In a real EMF device, there is an internal resistance. As you can see here, EMF device is nothing but the cell, and we know that cell is having their own internal resistance, that is called as internal resistance, and which is referred as small r, denoted by small r. So In a real EMF device, there is an internal resistance to the motion of charge carrier. If such a device is not connected in a circuit, so what will happen? There will be no current throughout the circuit. In that case, the EMF is equal to the potential difference across the two terminals of the EMF device connected in a circuit. So there is no current through it. If we consider that the current I flows through an EMF device, there an internal resistance small r and the EMF E and potential difference across its two terminals is nothing but V. So we can say that potential difference will be nothing but E minus IR. See, as I have explained you that if there is no obstacle, there is no resistance, so V is equal to E only. But if there is an obstacle, there is a resistance, so, and we know that an EMF device or cell is having their own resistance, that is internal resistance. So overall potential difference will be nothing but E minus IR. What is IR? That is, according to Ohm's law, V is equal to IR. So across that internal resistance, the potential difference will be nothing but IR. Fine. So finally what we can say that V is equal to E minus I small r. Now if you remember, now first of all labeled it as equation number 1. Now if you recall Ohm's law, what is Ohm's law? Ohm's law said that V is equal to IR, and we are having our in equation number 1, we are having V with us. So if we substitute this, if we apply the Ohm's law, so our equation number 1 will become that IR is equal to E minus I small r. Now why we are doing this derivation? Because we have to derive an expression for the maximum current. Okay, so what we can do, see, you can take the common terms that having the current at one side and the remaining at the right hand side. So if you take the current related term at the left hand side, so what you can have here, capital I capital R plus capital I small r is equal to E. Yes, now what else you can do? You can take out the common, that is I common out of the bracket, and in the bracket what you can have, that I in the bracket capital R plus small r is equal to E. So finally you can derive I. So I can be nothing but I is equal to E upon R plus small r. So this is the formula for the current, but this is only the current, it is not the maximum current. When you will get the maximum current, just think about it. See, resistance is nothing but the obstacle. Obstacle means what? Opposition offered by the resistor. So obstacle is what? That controls the current. If there is no obstacle, so there will be flow, the flow of current will be maximum if there is no obstacle, but resistance is the obstacle here. So when you will get the maximum current, just think about it. Yes, when you can take that the internal resistance, where the resistance is 0. So if the resistance is 0, thus the maximum current that can be drawn from the EMF device is when resistance, that is the external resistance, is equal to 0. If external resistance, external obstacle, there is no external obstacle, so current will be at their maximum, at their peak value. Current can flow maximum in the circuit. So this will be I max is equal to epsilon upon small r only, because capital R we have taken it as 0. So this is the maximum condition of the R when you can get the maximum current that can be drawn from the EMF device. So it is when it will be happen, when you will keep that capital R is equal to 0. So here we have derived the maximum for current. So this will be equation number 4. This is the maximum allowed current from an EMF device or a cell This decides the maximum current rating of a cell or a battery. So this is all regarding the EMF of the cell, potential difference, internal resistance, and last we have derived an expression for the maximum current from an EMF device by using applications of the Ohm's law. So let's stop here, and this is the main topic, and the question based on these topics may ask you in the exam. And as you have seen the learning objective, so you have to focus on the learning objectives and you will have all the answers of that objectives. So here